This is AQA GCSE Chemistry. This is a dual and triple award topic, and we are starting to look at the periodic table. This is video number 1. I'm going to recommend that you pause on each activity and have a go at it for yourself before reviewing on the rest of the video. So, in this video, we're going to look at how the periodic table developed over time, essentially the history of the periodic table, and also looking at how predictions can be made and how they can be used to help support scientific ideas. So, for context, if we go back several hundred years, ancient Greece, several thousand years actually, there was an idea that all of the elements that existed were fire, earth, air and water, and everything that existed was a combination of those four to some degree. Now that changed a lot, and it's changed very rapidly over the last couple of hundred years. And in this video we're going to start to take a look at some of those significant changes. Going to start by looking at John Dalton. He was a Manchester-based scientist, and he put the elements in order of their atomic weight. So you've got a copy of his table here. What similarities can you find between this table and the modern periodic table? And what key differences can you find? So in terms of similarities, I would be looking at the fact that we have many names that look familiar. Hydrogen, carbon, oxygen, phosphorus, sulfur, iron, zinc, copper, lead, silver, gold, mercury. Every single one of those still exists on the modern periodic table. There are some that don't, and we'll talk about those in a minute. In terms of the key differences, there are far fewer elements here. There are 100 and something elements now. We are looking here at around 20. Now that's because many hadn't been discovered yet. There were also different symbols. We have quite a systematic system for symbols now. It might be the first letter, the first two letters, a combination of letters from the name. There might be symbols that bear no relation to the modern name, but it's always letters. Here we're using circles, sometimes a black circle, circle with a dot, circle with a line, circle with a cross. Actually a lot harder to try to remember those symbols, which is one reason that may have been changed. Some elements on here no longer appear on our periodic table. Lime, barytes, potash, and that's actually because these were not elements. They've subsequently been able to be broken down more into compounds. And the numbers don't match with the ones on the periodic table. Now, these are in terms of atomic weight. And we don't use atomic weight anymore. We now use atomic mass. Atomic number. An atomic number is the number of protons. This was the atomic weight as they could measure at that time. Now from here, from John Dalton, we moved on to John Newlands. So have a read of this and then have a go at these activities. So John Newland liked the idea of using atomic weight at that time, but he noticed a pattern that every eighth element had similar properties, and Newton came up with his law of octaves. Now, the biggest changes that we see here is that it is more ordered. We've also got the same symbols as the modern table, and we're starting to see similar elements grouped together. And that ties in with the next question, because I've picked out a couple of examples here. Lithium, sodium, potassium, rubidium, cesium are all grouped together, just as they are in a vertical group on the modern periodic table. Similarly, fluorine, chlorine, bromine, iodine. Now, they are not the only examples. You could find some of group 2 are together, some of group 6 are together, but that is more than ample illustration of how progress had been made and similar elements were grouped together. But John Newland's table was not without its problems. So have a think about these questions. And we're looking here for examples of elements grouped together that should not be. Now, bear in mind, you will be provided with this table if you're asked to answer a question like this. And you will also have a periodic table, so you can compare and contrast what are together that should not be. As you get more confident with your chemistry, some of these will stand out much more. Potassium and copper together. Potassium, an incredibly reactive metal that ignites on contact with water, and copper, a metal that doesn't react with water to the point it can be used in water pipes. We've also got silver in that same group, which is an incredibly unreactive metal. And we've also got down here iron with oxygen and sulfur. A metal and a gas grouped together. That does not make a huge amount of sense. So I've put those two examples down, potassium and copper, or oxygen and iron. They shouldn't be grouped together. You might also be asked about other problems that we recognise within this periodic table. And actually the big one that stands out is that there are elements sharing a space. Cesium and lanthanum. Rhodium and rubidium. So that wouldn't work if they're stuck together in a box. That doesn't give a huge amount of confidence that this is a table that's going to work. Now, going to move on and we're going to take a look at Mendeleev, who essentially came up with the table over 100 years ago that now is still used. So have a read and then have a go at these questions. So Mendeleev's table proved to be so successful it's still around today. It's been adapted, it's been added to, but everything that we now use is based on the work that he did. Mendeleev still placed them in order of atomic weight. That's an important distinction. But he made a couple of changes. Mendeleev left gaps. Why would he have done that? Well, Mendeleev knew that there were elements that had not yet been discovered that must fit in, that would have atomic masses that would fit within that space. And that was a huge, huge step forward. And leaving gaps did actually help him to prove that his periodic table was effective. Because not only did he leave a gap, but he predicted the properties of those elements. When those elements were subsequently discovered, sometimes decades later, the properties that he had proposed were exactly as he had suggested. Mendeleev's table was still not perfect. Have a think about this question and we'll talk about the improvements he made and how it moved forward. So he put them in order of atomic weight that we now call atomic mass, but it didn't quite work. So we had to do a little bit of swapping around. He didn't quite know why, but you may be asked to find examples in the modern periodic table where in order of atomic mass, the elements would be in the wrong place. The two examples that you are likely to discuss are argon and potassium. Now, in terms of atomic mass, argon would be in group 1 with lots of reactive metals, and potassium would be in group 0 with lots of unreactive gases. Mendeleev swapped them. The other example that commonly comes up is tellurium and iodine, which does exactly the same thing. But I think this one illustrates far more why the change was needed, because we're aware of the properties. Now, actually, as the periodic table has been adapted and improved, we now put them in order of atomic number. And that does put these in the right order. That takes us to the end of this video. Thank you for listening and goodbye.